a password, at times Zoom could be kind of inconsistent. There's not any password. So I believe everyone should be able to join now. Yep, everyone should be able to join now. So oh, somebody said the Zoom link on Canvas asks for password. I didn't set any password. Maybe you can, I normally send a notification for meeting, and it's the same link. So probably you could be clicking on notification for meeting. Oh, thank you. Sorry about that. At times, Zoom could be in kind of inconsistent. Okay, so what I'm gonna do now, I'm gonna share my screen. Like I said, I told you the other time, I'm basically gonna start from, where we stopped yesterday. Give me 1 second while I put that up. Now, I'm basically gonna be kind of fast today, but you know what? I can assure you, you're basically gonna be fine. Okay, so this is where we're gonna start from today, independence. And of course, let me tell you this, if you really want to understand the notion behind independence, you first need to understand Cartesian product. Okay, basically, because the Cartesian product actually provide a background, okay, for the existence of independence. So what I'm going to do, let me first quickly walk you through Cartesian product so that you'll be able to link that with independence. Okay, so I'm basically going to share my whiteboard now, which I need every one of you to actually confirm if you're actually seeing my whiteboard. Is everyone seeing my whiteboard? Are you seeing my whiteboard? Okay, thank you so much. Now, I was talking about Cartesian products. Okay, I was talking about Cartesian products. Cartesian products actually play a huge role in independence. And what do we actually mean by Cartesian products? Okay, when we have, X that is taking a kind of, you know, uh, you know, a subset in X1, a sample space in that, and we have Y taking sample space, lies in this, and we basically want to cross X and Y. Okay, crossing X and Y, we basically gonna have this such that, of course, S actually come from this, and Y actually come from this. An example of this guy now is basically the example of that is basically when I have X probably to be 1, 2, okay, and I have Y to be 3, 4. Okay, take a look at that. And I actually want to do Cartesian products, okay, which is basically the set of order paired. So if I basically want to do this, I can put an X here where I got 1 and 2, okay, and Y where I got 3, 4, okay. Then I need to start crossing that, okay. So if I start crossing that now, I'm actually going to be using this guy to multiply that guy, and eventually what I'm going to have is going to be 1, 3, okay. I'm actually going to have 1, 4. I'm going to have 2, 3, okay, and I'm actually going to have 2, 4. So take a look at that. Now, the Cartesian product now, okay, the Cartesian product now, okay, is basically, when I claim my board now, okay, the Cartesian product now is basically S star Y, okay, the set of that now is basically 1, 3, okay, 1, 4, okay, 2, 3, okay, and 2, 4, okay, that is the Cartesian product. And let me tell you this, there is something that we call the cardinality, okay, cardinality of a set. Okay, when I talk about, because a Cartesian product is a set, okay, the cardinality of a set actually means the number of elements in that set. Okay, the cardinality of a set means the number of elements in that set. Okay, now what I'm going to do now, if I want to say the cardinal, the symbol for cardinal is this guy. So when I say cardinality of X, it means how many elements do I have in X? That is basically going to be 2. What is the cardinality of Y? How many elements do I have in Y? That is going to be 2. Now, what is the cardinality of the product, of the Cartesian product? The cardinality of the Cartesian product, if you can now, basically going to be 1, 2, 3, 4. So this is going to be 4. Okay. Now, when you take a look, okay, somebody asked a question now. Let me look. Somebody said, do the two sets we take the product have to have the same cardinality? No. Okay. They don't need to have the same cardinality. We could have the number of the cardinality of each of that may be different. At times may be the same. There's no problem. Okay, I think I've answered the question now. The person who chat with me, so they don't necessarily mean to have the same number of sets. They could have different number. Okay, now but you know what I want to use cardinality to do? I basically want to use cardinality to explain the notion behind independence. Now, right now, you're basically going to see that 2 multiplied by 2, that will give us 4, right? Now, what does that implies? It means what that implies, the takeaway from here now, okay, or the takeaway from here now, okay, is basically, okay, telling us the cardinality of X, cross Y is equal to the cardinality of X multiplied by cardinality of Y. Okay, this is the takeaway. Okay, and this is what we basically need to justify whether X and Y, okay, whether X and Y are actually, they are independent. Okay, because for X and Y to be independent, we must be able to establish the fact that the probability of the joint, okay, of the joint of X and Y must be equal to the products of the marginals. Okay, as you can see here, you can see it in the Cartesian product now, you can actually see that the cardinality of that now equal to that. Okay, so somebody said it's cardinality of X multiplied by cardinality of Y equal to cardinality of the product only if X and Y are independent. I'm going to tell you now, the moment that's old for X and Y, then we're going to say they are independent. Okay, we're going to say they are independent. Okay, now this is a cardinality. Okay, mathematically, this is how we define cardinality. Somebody asked question the other time about what if they have different number of items, and then there's no problem. Take a look at this. That law is going to hold. Okay, now take a look at this. If I have X, if X will have 1, 2, 3, okay, and Y probably has 2, 4, okay. Now the cardinality of X here is 3. The cardinality of Y here is 2, okay. And when you cross that out, the cardinality of that is going to be 6. That's what I'm trying to say. By multiplying 3 by 2, if you cross that out, okay, if you cross this guy out with that, you're basically going to have 6 elements. That's what we mean. Okay, we're basically going to have our 6 element. That is exactly what we mean. Okay, now I'm going to walk you through another example now. Give me 1 second. You're going to basically see what the connection, they have. But before I go into the connection between the cardinality of a set, okay, and, and independence, I think I need to first also tell you I need to tell you this. What if we have an empty set? Okay, what if we have a set A, or probably 1, 2, okay, and we have a set B, okay, it's empty. Okay, now if you cross that, okay, if we cross that, okay, we're basically going to have empty. Please take note of that. When a set is empty, when you cross it with another set, okay, the set of the product now is basically going to be empty. Now in that situation, the cardinality of A here is 2. The cardinality of B here, okay, because there's no element, It's basically going to be 0. Okay, now the cardinality of the cross. Now, if you take a look at this, we know it's 0. And if you want to confirm again, you can say cardinality or a if you multiply that by the cardinality of B, okay, you're basically going to have 0. Look at that. So I want you to take note of that. Okay, and we can have a situation where, and in cardinality, the commutativity does not hold. In cardinality, A cross B is not the same as B cross A. They are not the same. Okay, and we have condition under which they can be the same. The condition under which they can be the same is only when A equal to B, because we could have situation where the elements in A and the elements in B, they have exactly the same. Apart from having the same number of elements, the elements are exactly the same, which I'm basically going to show you now. For instance, if I have X, if it is 1, 2, and I have Y, and it's also 1, 2, look at that. Here, X equal to Y. Okay, in this situation, X star Y would be equal to Y star X. Okay, commutativity. Okay, commutativity hold. Commutativity actually hold here. So take a look at that. I just wanted to take note of that. And you know what? You may want to also talk about the power of a set. What if I ask you? Okay. Somebody said, give me 1 second. I'm actually gonna check my chart now. Somebody, even though AB is not always equal to BA, is the cardinality of AB always going to be no? This is what happened. The cardinality of AB is not equal to BA, except if A and B as equal, they have this exactly the same elements. And that is what I just showed now. Look at that. If you have 1, 2, 1, 2, the same element, okay, then this is the only condition under which the commutativity hold. Okay, I think I want that person to take note of that. Okay, now for the power of a set, okay, because what do we mean by power of a set? The power of a set, actually means, is the possible, okay, number, the possible number of subsets, okay, subsets in a set. That is what we mean by the power of a set. But you know what? Mathematically, we're going to say the power of a set is basically, we actually going to use a formula called the power of a set A, for instance, is going to be 2 raised to power the cardinality of A. Okay, the power of a set means 2 raised to power cardinality of that particular set. Okay, if I have sets, for instance, take a look at this, where I have 2 elements, the power of X now is basically 2 raised to power the cardinality, and that would be 2 raised to power 2. That would be 4. Okay, that would be 4. I also wanted to take note of that. Okay, now the next thing I quickly want to explain, I want to walk you through example, okay, on how you can actually link the cardinality with independence, okay, because I want to spend more time on that, because what actually determines independence in statistics is very, very crucial assumption, a very, very essential. And because this is the theory of statistics, and I actually want to, want you to say the linkage between the cardinality of a set and the notion of independence. I want us to have another example. Suppose, okay, suppose we chose a pair, okay, of, fear, a fair or two-sided, okay, two-sided, dice. Okay, you toss a pair, and in which, okay, one of the dice, in which one of the dice, okay, is red, okay, in which one of them is red, and the other is black, and the other, okay, is black. Okay, now take a look at this. This is an experiment right now. Now, in this experiment, we basically need to know the support. Okay. Since we are actually talking about, in fact, let me make it a 4 so that you will be able to, let me use a 4-sided instead of 2-sided. I'm going to use a 4-sided. Okay. Now take a look at it. Now we need to for define what is the random variable x. That is the outcome. Okay. On the red. And since I'm talking about 4, okay, the outcome of the red is basically 1, 2, 3, 4. Look at that. Okay. Now what about y? The outcome on the black, the outcome, okay, on the black is also going to be that. It's also going to be 1, 2, 3, 4. You remember we needed to state our sample size. I mean, our sample space, right? I told you, right? The sample space here, right? It's actually going to be finite. Okay. I need everyone to confirm again. If you're still hearing me clearly, is everyone hearing me clearly?
Yeah.
Okay, thank you so much. Now, take a look at this. We've defined our x, we define our y. You have the support of x, you have the support of y now. Okay, now what I'm trying to say here, let's say x1, the sample space for that, and x2 the sample space for that. And don't forget what I'm trying to say. We're trying to say x actually lies in x1 and y actually lies in x2 because there must be sample space. Now, what is the question? The question is, what is the probability? Now, if you have copied this now, I need a space. I want to write. So you were given this experiment now. You've already defined. You've defined your, support for x and y. Okay. Now the question now is, what is, okay, the probability? Okay. What is the probability that x, okay, takes, okay, on a particular value, lowercase x, and y, okay, takes on a particular value, lowercase x. Okay, that is what we want to find given this experiment. Okay, now mathematically speaking, if I want to write that in terms of notation, you know what I'm going to do in terms of notation? And basically what I want to have, I'll calculate is this. Probability that this equal to this and this equal to that. Okay, that is what which is a joint probability. This is what we call joint PMF, the joint probability mass function, because you are having x and y. Okay, you are having x and y. Now, if you really want to solve this problem, okay, you're basically going to use the idea of Cartesian products. Okay, you need to use the idea of Cartesian products. Okay, now let me tell you this. You know that the support of x is 1, 2, 3, 4, right? The support of y is also 1, 2, 3, 4. Therefore, we need the support of the Cartesian products. I'm going to say that again, because the support of the Cartesian product is basically going to give us independence. I'm going to say that again. We need the support of Cartesian product. The support of Cartesian product will give us independence, which means by using the idea of Cartesian product now, we basically want to get a support x. I'm going to show you. We basically, oh my God, we basically want to get this guy, which is x1 cross x2. That is what we want to get. We're basically going to cross this. Okay, we're basically going to cross that. I'm going to say that again. The support of Cartesian products is basically, going to indicate that x and y are independent. Now take a look at that now. If you want to cross that out, I'm basically going to have 1, 1, 1, 2, 1, 3, okay, 1, 4. Okay, so 1, 1, 1, 2, 1, 3, 1, 4. I'm going to have 2, 1, 2, 2, 2, 3. Okay, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, 4, 1, 4, 2, okay, 4, 3, and 4, 4. Look at that. That's what I'm going to have. And you know, if you count that, automatically it's going to give you 16. You're basically going to have 16. Okay, you're basically going to have 16. Now, if you have 16 right now, you're basically going to see. The other time when I was talking about X, the cardinality of this is 4, the cardinality of that is 4, automatically the cardinality of this guy now is basically going to be 16. That is why the total number of elements you have in that is going to be 16. Now, if I want to answer the question of the probability now I want to award an extra credit now. Oh my God, I want to award an extra credit now. Can somebody tell me what is the probability of this guy now? Since I have the sample space for the Cartesian product, can somebody tell me what is the probability that X take a particular value and Y take a particular value? Can somebody tell me what that probability is?
1/16.
Oh my God, those of you that say 1/16, you guys are fantastic. Send me a message for extra credit. Good job. So it's basically going to be 1/16. Okay. And if you want to find the probability of each one, okay, you know, if you want to find the probability of each one of them, it's basically 1/4. Okay, the probability of Y, because you have 4 elements, 1/4. Oh my God, look at that. Independence has come up now because you know why? If the joint probability can be written as a product of the respective probability, then X and Y are independent. Now, in this case now, I'm actually going to conclude that X and Y are independent because 1/4 multiplied by 1/4 will give me 1/16. You can now see now we are now using the idea of Cartesian product to figure that out. Is there anyone who doesn't understand how to go about independence right now? Is there anyone?
Can you repeat that, please?
Okay, what I'm trying to say in essence now is that if you look at the X1, we have 1, 2, 3, 4, right?
Oh,
When you
sorry,
look,
just the last part when you said if the product of
oh, okay, okay. Now this is what happened. X and Y are independent if the probability of the joint, you know, this is the joint, can be written as a product of the respective probability. Okay, if it can be written as a product of the respective probability, what I mean, the product of the marginals. This guy here is a marginal probability of X, marginal probability of X, and this guy here, the marginal probability of Y. Okay, so when the probability of the joint actually give you the product of the marginal probability, then you're going to conclude that X and Y are independent. That is exactly what I mean. Does that make sense to you right now?
yes.
Okay, thank you so much. Now I want to go into the material now, since you now understand the notion of independent now, okay, how it relates to Cartesian product. Give me 1 second. I'm going to pull up my slide now. Um, okay, now you know we've only done that for 2 sets, right? For 2 variables. Now what you are seeing here now is a generalization. What you're seeing here now is a generalization. Okay, I think a chart came in. Let me look at my chart. Somebody said, can you quickly show an example where the cardinality of the Cartesian product is not the same as the product of the cardinality? Okay, that's a very good question. He said, can I show the example where the cardinality of Cartesian product is not the same as the product? Let me tell you this. The moment the 2 sets are not empty, I'm going to say this again. The moment the 2 sets are not empty, okay, the cardinality of Cartesian product, okay, is always going to, the cardinality of Cartesian product will always going to be equal to the product of the cardinality of each. Okay, so I just wanted to take note of that. Okay, it's always going to be equal, always going to be. Okay, it's always going to be. And the only condition under which it's not going to be is when they depends. If the two variables depend, because we're talking about independent now. Okay, but if the variable depends, then that is not going to hold. I'm still going to show you an example of that. You're basically going to see. Now, when you take a look at this now, okay, this is a generalization. I have x1 up to xn. I have number of variable I have is n. And this guy now is a joint for that. Now, this guy is a cross product. What that guy means is f of x1 multiply by f of x2 until you get to f of xn. That is what it means. This is writing that in short form. And each of that, don't forget, means the probability means this guy here. Okay, so that is a generalization. Okay, because we could have situation where so many variables are independent. Okay, so I think that is the explanation. It's just a repetition all this. It's just repetition, but there's something I'm going to show you now. Somebody who has a question now, take a look at this. We have criteria before we can say, look at this. If the support of the random variable is a Cartesian product, then our conclusion is going to be they are independent. What do we mean by support? You remember the other time, the support is actually the space of X, the space of the products, space of the products. The other time we got 16, okay? The space of the product now, that space, the values that space can take, like the value, okay? So the moment if the support is a random vector of that random vector is a Cartesian product, then they will be independent. And this actually implies the second one. Because if this guy hold, the second one is going to hold. The second one is the one that's okay. Then the PMF of the joint will be equal to the product of the marginal. That's exactly what we mean. Otherwise, what are you going to say? They are not independent. Not independent means they depend. Okay? I just want to take note of that. So for uniform, it is. Okay, if you follow what we have done. Okay, it is. Okay, you follow what you have done. Now this is a situation. Somebody said I should show an example. This is a situation where the x1 and x2 are not independent. Look at that. Look at the range. Because of this range here, look at the range where x2 is depending on x1 because it's a x1 less or equal to x2. Okay, because of that connection, we basically going to say in this situation the support is not going to be Cartesian. The support here is never going to be Cartesian. Therefore, because of that, you don't even need to go and verify the second assumption. Okay, so just take a look at that. Okay, now the next thing objective I want to talk about in this material is something that you've done before, which we call factorial. Okay, now some of you in high school, when you see 5 factorial, it means 5 times 4 times 3 times 2 times 1. It's talking about the product of a particular sample size that is actually going down. Look at that. Which this is the generalization now. Take a look at that. Okay, so we're talking about, we use that in arrangements. Okay, so take a look at that. If I'm saying how many ways can I arrange something in a row? Okay, now this guy now, that is what it means. Okay, so that guy is actually mean, where I start from 1, 2, 3, 4. Okay, if I'm talking about 4 factorial, it means I'm actually going to do 1 times 2 times 3 times 4. That is what it means, which is going to be 24 here. And you also need to take note the 0 factorial equal to 1. Okay, because why 1? We're talking about how many ways can we have that. We only have one way to report an empty, something that is empty, an empty box. It's only one way. That's why 0 factorial is basically equal to 1. Now, apart from that, we also have what we call permutation and combination. Okay, now this is an example of permutation. What do we mean? In permutation, when order, okay, do matter, I want to arrange, and our order do matter, of course, I'm actually going to use permutation, okay, which is this guy now. Okay, Now I want to select K out of N. Okay, I want to select K out of N in such a way that order do matter. Okay, I'm actually going to use that. But situation where order do not matter, I'm actually going to use combination. This is a combination. Combination. Okay, when order do not matter, I'm actually going to use that. Take a look at that. And they have a connection. You know, the other time this guy was the permutation. So it means permutation divided by K factorial will give us combination. That's exactly what we mean. They have a connection. Okay. So, and you know what? You can actually prove that this guy equal to that. Okay. If I want to prove that now, this guy is a short way to write combination. Okay. So it's going to be N factorial divided by K factorial N minus K factorial, which is this guy here. If I want to write the right hand side, it's going to be N factorial divided by N minus K factorial. Then I'm going to subtract. I'm going to do N minus into N minus K factorial. Let's simplify that. So N factorial divided by, this is N minus K factorial. And here is going to be N minus N plus K factorial. See, that cancel that. What does that give now? It gave you F factorial, N minus K factorial, K factorial, which is the same thing as this guy here. Now you can now see they are the same. Okay, we're just having a mathematical proof. That's exactly what we are having. Take a look at that. Okay, that is what we're having. Okay, so that is how to show that. And you know what? I think I just show you. This is a permutation. That's a combination. Don't forget, this is the one that is, N factorial divided by N minus K factorial. And this is the one that is N factorial divided by K factorial N minus K factorial. So I just wanted to take note of that. Okay, take note of that. Okay, now, from here now, you've heard about binomial expansion. If I have A plus B raised to power N, there's a general formula for that, which is basically this guy here. Okay, A plus B raised to power N is basically that. And of course, in this binomial expansion, you're basically going to see that this guy is a combination that I talked about the other time. Okay, selection when order matter. Take a look at that. So I just trying to tell you, because we're still going to talk about binomial distribution. Now, we want to have a kind of generalization. I think what I'm going to do today, I'm going to spend a lot of time in this material. Maybe I'm going to study other material tomorrow because I want you to understand. That's why I don't want to rush. I really want everyone to understand. This is a theoretical course. And that is why I'm actually going to take my time. Now, let me quickly explain this. The other time I told you, we have Bernoulli, right? Bernoulli and binomial, we use them to model a dichotomous outcome that have to, experiment that have two possible outcome. For Bernoulli, and you know what? Bernoulli is basically used when when we have one triad, n equal to 1. But why binomial is when you have more than one triad. But let me tell you this. If x1 follow a Bernoulli distribution, okay, and I'm considering the sum of x1, x2 up to Sn, okay, I want to know what is the probability distribution of y. You remember yesterday when I was walking you through change of variable? Originally, we were at x1 up to xn, where each of the x represent Bernoulli distribution. Now, when we now add that together, okay, what are we going to have? It means we need to seek the probability distribution of y. We already know the probability distribution of x1 up to fxn, each of them is Bernoulli. Okay, now how we're now seeking to get the probability mass function for y. I told you yesterday, this is a short way to write binomial distribution. Okay, n comma p. N is a number of trials and p is a probability of sources. Okay, now a special case of binomial is Bernoulli. When n equal to 1, I'm basically going to have bin 1p, which is the same thing as Bernoulli p. Okay, take a look at that. And that's exactly what I'm talking about here. Take a look at that. Okay, that's when the trial number of trial equal to 1. Okay, number of trial equal to 1 is just like when I try once, when I have one business, okay, it's either I make profit or I make loss. Okay, if I try once, just one business, it's either I make profit or I make loss. That's it. That's what I mean. Okay, now, right now, we now want to add, we want to use the notion of independence to be able to see if we have, if each of these variable is Bernoulli, and when we had all of that together, okay, we want to see what is the probability distribution for y, the new variable. Okay, we want to use the idea of independence right now. Okay, using the idea of independence, what are we actually expecting? Okay, using the idea of independence, we want to find, we need to first find the probability of joint. In the independence, the probability of joint is equal to the product of the marginal probability. If you take a look at this guy now, it's basically telling you the probability of x1 equal to small x1 multiply by the probability of x2 equal to small x2 dot 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 until you get to the probability of xn equal to small xn. So this guy is a product. Okay, when you see this sign, it's actually represent products. Okay, now if we want to find the product, don't forget we say y equal to x1 plus x2 until we get to xn. Okay, if x follow Bernoulli, okay, with parameter p, okay, if that, don't forget the other time I showed you f of x is basically p raised to power x 1 minus p raised to power 1 minus x. Don't forget the range, the range of x, the range of x is actually 0, 1. Okay, now in that case, if I actually want to find the probability of join now, then I'm actually going to find the products of this. Okay, now finding the product of that is more or less like I want to put the product for pxi 1 minus p 1 minus xi. Now, if I want to have this one in n term, okay, it's basically going to be p raised to power summation xi and 1 minus p raised to power n minus summation si. Okay, then I'm going to say let k be summation si. That's how I have this. Look at that. Okay, if you are summing that in n term, okay, we want to find the products of the marginals for us to use the idea of independence. Don't forget we are seeking to get the probability for the response variable y. We are x1 plus s1 follow Bernoulli, s2 follow Bernoulli, and I have n number of them. Now take a look at that. So that was how we got this. And another thing you're now going to consider, in how many ways can I actually select something out of something in such a way that order do not matter? I need to consider that. Then I'm going to multiply this entity by combinatorial. Oh my God. You basically now say, now that is why we have this. Okay. What do you think we are actually doing now? We multiply what we got by that. And you know what? This guy now, we now have a binomial distribution, which means when we have an x1 plus x2 up to xn follow Bernoulli distribution, the addition of that, the sum of the Bernoulli is basically going to lead to binomial. And that actually confirms the fact that, that confirms the fact that, Bernoulli is a special case of binomial and binomial is a general case of Bernoulli. Oh my God, when n equal to 1, that's a Bernoulli. When n is more than 1, then we basically have binomial. So what I'm trying to tell the world now, if x1, x2 up to xn follow Bernoulli, the addition of that, why now we now follow binomial with parameter np, when xi follow Bernoulli with a parameter P. Okay, therefore the Y, and don't forget Y is actually the sum of Bernoulli. What have we done now? We have used the knowledge of independence to figure that out. Take a look at that. Okay, now we now have a binomial distribution. Okay, the binomial distribution now, okay, is X follows binomial distribution with parameter NP if f of x equal n combination s, p raised to power s, 1 minus p raised to power n minus s. What is the support of x here? The support of x is 0, 1, okay, is 0, 1, 2 until you get to n. That is going to be the support, okay, 0, 1, 2 until you get to n. Now, if I want to find the mean, don't forget, on Monday, I walk you through mathematical expectation, expected value of x. When s is discrete, it's basically going to be summation of x, f of x. Now, what is the f of x now? The f of x is binomial. Look at that. That's what I plug in, right? Plug that in, right? Okay, then I'm going to explain the third one now. Okay, when you want to explain the third one now, I'm starting s start from 0. When I plug in 0 to where I have x, because of x here, the whole thing is going to be 0. So therefore, I can start from 1. That was why I decided to start from 1. Because when you start from 0, when you plug in 0, everything is going to be 0, then plus this one now. So it's better I actually consider this. Now, when I consider this now, I'm here now. Okay, don't forget, what is n combination s? It is this guy here. Look at that. Using the combinatorial analysis. Okay, I just wanted to take note of that. So this guy is basically this guy. You see that now? That is that guy. Okay, now we are here now, right? We're here now. Now, the next thing we're basically going to do now, okay, is if you take a look at this is n factorial, okay? This is s factorial. This is n minus x factorial. Do you actually know that I can do something here? Okay, do you know x factorial? I can write it as x into x minus 1 factorial. Why? 5 factorial can be written as 5 times 4 factorial. Look at that. So my s factorial here, okay, is basically going to be replaced by this. Okay, and if it is replaced by that, you're going to see that the x here is just going to cancel this guy out. Because of that, I'm basically going to have this now. Look at that. That is the only thing that changed. Okay, take a look at that. So we have this guy now. Now, when we have that guy now, the next thing that we're basically going to do, that is what I have here is see what I have here right now. Okay, now when you take a look at what I have here now, the n factorial here, I can also say n factorial equal n into n minus 1 factorial. Just like what I did the other time that I said s factorial equal x into x minus 1 factorial. So here, I'm actually going to put this, look at that, where the n here is going to come out. The n is going to be out of the integral summation sign. Okay, now I have this n here. Now, how do I get p out? I'm going to tell you. Here I have a p raised to power x. I can do p raised to power x into this p raised to power minus 1. Okay, this can still cancel itself out. You know that, right? So this p here is the one here. This p raised to power minus 1 here, I can combine that with this guy here. Then you're going to have this guy. That will be p raised to power x minus 1. Look at that. If you look at that. Okay, now you now have this now. And when you take a look at what I have inside here, okay, you basically are going to see that is the same thing as this, which is sum up to 1, because the sum of probability have to be 1. And 1 multiplied by NP is basically going to be NP. And therefore, NP is the mean of binomial distribution. So if X follow binomial, now I wanted to say this. If X follow Bernoulli with parameter P, expected value of X is P. But if X follow binomial with parameter NP, the expected value of X is NP. Look at that. The difference is just N here and NP here, in such a way that when N equal to 1, the mean of binomial become the mean of Bernoulli. And that was why we call it a generalization. Take a look at that. Okay, so so far so good. Like I said, I'm only going to focus on this material. Today's material, I'm going to start that tomorrow. I'm trying to take my time. I don't want to rush you at all. I know this is a theoretical course, and of course, I want to walk you through that, line by line, so that you will be able to understand. I want everyone to gain. Okay, is there anyone want to ask question today before I go? Is there anyone who need clarification? Is there anyone? Okay, before, if you really understand today's lecture, I need you to say comment yes or say yes. If you really understand, like, okay, thank you so much. Now, before you go, like, you can log out, but I quickly want to give a clue on assignments. I've been receiving messages from you about infinity. There's a particular question in number 4 where we have infinity stuff, but I'm quickly going to remind you of what we did in high school. Okay, I'm going to remind you of what you did in high school. Okay, in high school, if you have if A equal maybe 1 or 2, 3, okay, and you basically probably you want to sum. You have 1, I'll give me 1 second. You have 1 plus 2 plus 3, and you want to sum that. Okay, now if you want to sum 1 plus 2 plus 3, of course, you basically going to use Taylor series. But what if in a situation where you just have something like um x raised to, maybe x raised to power c, okay, and where c can be 1 2 uh 1 2, or let me just say, let me introduce a summation. C start from 1 to infinity, 1 2 and so on, like that, in such a way that you have this is something as having x raised to power 1 plus x raised to power 2 plus x raised to power 3 and so on, like that. And you want to sum that. Oh my God, do you remember sum to infinity in geometric progression, where a sum to infinity is a divided by that, where this guy is going to be first term, okay, first term. This is a common ratio. Do you remember that? That's a common ratio. The first time here is x, a equal to s. What is a common ratio? The common ratio is, is also going to be s, because s squared divided by s is to power 3 divided by s squared is going to be that. If I want to find sum in this case, sum to infinity now, it's basically going to be x divided by 1 man. Look at that. That is sum to infinity. So use this idea to solve problem 4, the one that where the support is to infinity. Okay, so a lot of you actually reach out to me, and of course we advise that you're actually going to use that knowledge. The theory of statistics actually have prerequisite, and they believe that you've done some kind of form of mathematics before you come here. You get what I mean? So this is going to help you out. Okay, you're basically going to use sum to infinity in geometric progression, geometric series. Okay, and you know what? Don't forget, when you are dealing with a constant, don't forget, for constant, the sum of for you to have a valid PMF, the sum have to be equal to 1. Okay, the sum have to be equal to 1. Okay, because maybe they may put a constant here, and they ask you to find the values of the constants, for you to have a valid PMF. Okay, the sum have to be equal to, you got to equate that to 1. Equating that to 1, then you only solve for B at the end of the day. Okay, I hope that's really help. This is where I'm actually going to stop today until tomorrow. Then I'm actually going to come your way. If I want to put this recording on course canvas, I'm still going to call it lecture 1, only that I'm going to say lecture 1 part 2, because I'm still using the material for yesterday, and that is why I'm going to call it lecture 1 part 2. Okay, so I don't want to cause confusion, and that is the reason why I say that. So the recording for today, I'm actually going to call it week 2. So it's going to be lecture 1, okay, part 2, because we've just finished what we started yesterday. Okay, make sure you actually stay safe and have a very lovely day. Bye for now, everyone.
Thank you.
You're welcome.